Okay, welcome back to the next video, which talks about trigonometric identities and also solving trig equations. So, trigonometric identities are relationships between trig functions in which the values or the outputs are identical to each other. I'm going to show you a set of trig identities that we're going to start with. Take a look at these. These are the common trig identities that we use in calculus. First set is the Pythagorean identities here. Sine squared plus cosine squared is equal to 1, and that's for, you notice the angle theta, so we could do the sine squared of 30 degrees, add the cosine squared of 30, you will get 1. These two are related to the original. If you were to take the original Pythagorean identity and divide both sides by sine squared, you would actually obtain this bottom one right down here. If you were to take the original expression and divide both sides by cosine squared, you would actually get this one down here. Here are some sum and difference formulas. We're not going to use those too much. Law of cosines, probably not so much. Even and odd identities. So the sine of, let's say, minus 30 degrees would be equal to minus the sine of 30 degrees, for example. These are the even and odd identities. Here are some identities that are very useful for reducing the power of sine, cosine, or tangent. Sine squared happens to be equal to 1 minus cosine of 2 theta over 2. Cosine squared 1 plus cosine of 2 theta over 2. And then we have the one for tangent. We certainly know these reciprocal identities, right? These are the very definitions of those three other trig functions. Here are the quotient identities. We already talked once about the tangent being sine over cosine. And these are the double angle formulas. Here's one we use very often. Sine of 2 theta is 2 sine theta cosine theta. And then cosine 2 theta, there are 3 different versions of that. And then there's a tangent also. So these are important. Some of them should be memorized. We should know the Pythagorean identities. We should know those because we do use those often. We should know the quotient identities. We certainly ought to know the reciprocal identities since they're the very definition. Some of the other ones we may need to look up. So let's take a look at solving a trig equation. And as we get into solving a trig equation, we probably will encounter situations where we need to use those trig identities to assist with the process of solving. So let's get started. And what I'd like to do is to solve a trig equation in which the output of the trig function is known. For example, the sine of theta is equal to a half. Now, I'm hopeful that you know the answer to this one. This one is one that you should have memorized. 30 degrees, sine of 30 is a half. But that's not the only answer. There are 2 primary answers that I'm looking for. Between 0 and 360 degrees. And then after that, there's an infinite number of answers beyond that because of coterminal angles. So if 30 degrees is an answer, what else must be an answer? 360 plus 30 gets you into the same location for the terminal ray. So therefore, that also should be a half. So how do we solve and find all of these solutions? Well, here's how we do it. The first thing to note is that if you look at the quadrant map here, you would realize that if your angle resided in here, and let's even just use the unit circle, the sine of this angle would be equal to the y value divided by the r value. And if r is 1, it's a unit circle. So the sine is just y. It's just the y value of maybe this coordinate right here. But look where you are in quadrant 1. All the y's are positive. For cosine, we would use the formula x over r. In this case, if it's a unit circle, just x. And notice that, again, we're in quadrant 1 where all x's are positive. So cosine should be positive. And finally, the tangent of the angle should be either y over x or, by identity, sine over cosine. Well, no matter how you look at it, it's positive over positive in both cases. Make a positive. So your sine, your cosine, and your tangent in quadrant 1 is all positive. Let's go over here. The sine of theta on a unit circle would be y, which is still positive in quadrant 2. The cosine of theta on a unit circle would be x, which is now negative because we're to the left. And the tangent would be y over x. That is positive over negative, which is negative. So in quadrant 2, I can assure you that the sine, any angle in quadrant 2 will come out to be positive, but the cosine and tangent will come out to be negative. Let's try the same for the other two quadrants. The sine of theta on a unit circle, that's y. But now we're in negative territory. The cosine of the units on a unit circle would be x, and we're in negative x territory. But the tangent should be y over x, which is negative over negative, which makes a positive. So the sine and cosine would be negative, tangent would be positive. And let's finish this off for quadrant 4. Sine is y, negative. Cosine is x, positive. Tangent is y over x. That would be y over x, which is negative. How do we remember this without having to do this every time? All trig functions are positive. Only the sine is positive. Only the tangent is positive. Only the cosine is positive. How do we remember this? All students take calculus. That's the way I remember it. So, all students take calculus. In fact, that's true of this class because we're in a calculus class. So all of our students are taking calculus. This is a great way to remember the quadrant map. So, let's talk about reference angles before we go ahead and solve this. If I were to put an angle into quadrant 2, and let's make theta equal to 150 degrees. Do you remember earlier in another video we talked about this angle briefly, which we call the reference angle? Think about what that reference angle would be for this particular example. Well, 150 and how many more get me to my 180, which is this side? It's got to be 30 degrees. It turns out that the sine of the big angle is equal to the sine of the little guy. The cosine of the big angle is equal to the cosine of the little guy. And the tangent of the big angle is equal to the tangent of the little reference angle. Sorry, that's over here. The only difference might be that the sine, cosine, or tangent might be positive or negative, and all you got to do is figure out what quadrant you're in. You're in a quadrant where sine is positive and the other outputs are negative. So if you want the sine, cosine, and tangent of 150 degrees, all we need to know is the sine, cosine, and tangent of 30. So the sine of 150 degrees has been shown to be positive, and it's the sine of 30. So it must be positive 1/2. The cosine of 150 degrees is in a negative territory for cosine in quadrant 2, but it's just the cosine of 30 degrees, which again, handy to know your sines and cosines. The cosine of 30 is square root of 3 over 2. You can look that up. The tangent of 150 degrees is negative because of where we are, but all you need for the value is the tangent of 30. Again, it's nice to know what these are. You can look it up on the table. It's a square root of 3 over 3. So here's how you get the sine, cosine, and tangent of larger angles. Use the reference angle. So all you need to know is the sine, cosine, and tangent of those smaller angles. That will give you the number part. The way to get the plus or minus part, just know what quadrant you're in. Okay? Now, how do we use this to solve a trig equation? The way to solve a trig equation, like that was presented to you, looks like this. If the sine of some mysterious angle happens to be 1/2, there's one thing we know right out of the gate, and that is the sign is positive. Where do we encounter positive signs? Well, it's true that all trig functions are positive up here in quadrant 1, and the sign is positive in quadrant 2, the sign is negative here and here. So I know that there are two answers now, one in quadrant 1 and one in quadrant 2. But what about this number over here? Remember, the number comes from the sign of the little reference angle. So you could write in the corner here that the sign of the little reference angle is a half. And by memory, or by looking it up, or even a little bailout procedure might be to move the sign to the other side where it becomes inverse sine. If you're going to do that, make sure your calculator is in degrees so that you get your answer in degrees. And your calculator will tell you the answer is 30 degrees. So we know two things. We know the quadrants where the two answers lie, quadrants 1 and 2, and we also know the reference angle. We're solving for the angles whose sine is equal to 1/2. Now what we're going to do is the last step. I refer to the last step as paste and measure. So it's not cut and paste. It's actually paste and measure. So let's go up here to the two quadrants that we've identified, starting with quadrant 1 here. In quadrant 1, I want you to paste in a 30-degree angle right here. And that's my reference angle. But normally, we measure angles from this initial side anyway. So the big angle in this case is 30 degrees. Now come over to the other quadrant you identified, which is quadrant 2, and same thing. Paste in a 30-degree angle. Now where do you paste this 30-degree angle in? I didn't mention that. Always up against the nearest portion of the x-axis, never against the y-axis. So we would put our 30-degree angle right in there, never in here. Okay, last step is measure. I need you to measure all the way across here to get this other angle. This is theta 1, and this is going to be theta 2. Well, think about it. Theta 2, if you were to go here and continue 30 degrees, you would get 180. So this must be 150 degrees. So the two solutions are theta equals 30 degrees and 150 degrees. But you know what? I think you should be able to do this in radians. Let's see if we can think it through in radians. Because the native unit of measurement in math is radians. So let's try this one more time. Theta prime is not 30 degrees, it's pi over 6. And if we leave the units off, that implies radians. Got my degrees up there. So let's do our paste and measure. So bold up the x-axis. In this case, quadrant 1, paste in a pi over 6, 180 over 6. It should be looking like a 30-degree angle. You can label that as theta prime is pi over 6, but we measure from here anyway. So theta is pi over 6. Got it. But come over here and do it again. Paste another 30-degree angle, theta prime, another pi over 6. Now watch how we measure it this time. So let's measure this big angle. We'll call this theta 1. We'll call this theta 2. Now say for the moment you went too far. You went all the way down here to this line. Wouldn't that be 180 degrees or pi radians if you went too far? So go too far and then back off by pi over 6. Back off means subtract. So let's see how many radians we got here. 6 pi over 6 minus 1 pi over 6 is 5 pi over 6. And see, we did that without having to convert back and forth between radians and degrees. So I do really want you to think this through in radians if you can. Not only that, those are not the only answers. Think about all the coterminal angles that would put the terminal ray in the same exact location. So the actual solution is right here. Pi over 6 plus 2 pi n, n being any integer you like, and 5 pi over 6 plus 2 pi n, where n is any integer you like. So n really represents how many full trips around the circle you've made before you add that pi over 6 angle in. N can be negative too. You can actually go backwards. So what's another solution here? Well, how about pi over 6 minus 2 pi. I made n negative 1. I went backwards. So minus 11 pi over 6 is another solution. So there are an infinite number of solutions, but I need you to identify those two primary solutions. And then if you simply add 2 pi n, you're going to pick up all the solutions. That's really the best way to do that. Okay, let's continue. We've solved a trig equation, but I want to look at some other cases here. What about when the parameter, the argument, isn't cooperating? If it isn't theta, it's awfully hard to work with. So let's try one. Let's try one that has a double angle in it. Let's try cosine. The cosine of, we'll make this one tough, 2 theta equals, and the left and right sides have to be equal to each other. I'm making this one a challenging one, but this one is an example from the book. Now, there's no way to solve this equation when the arguments do not match. So how are we going to make these arguments match? Best way to make these arguments match is to revert back to your trig identities. So let's take a look at some of the trig identities available to us. There's one right here that will help us tremendously. Cosine of 2 theta can be rewritten 3 different ways, but I think the best way is going to be the middle way right here because it has a sine of theta in it. And the rest of my problem also has a sine of theta. So by identity, the cosine of 2 theta is 1 minus 2 sine squared of theta. So let's see where that leads us. So I'm going to replace the cosine of 2 theta with its identity. And hopefully now the equation has all sine of theta in it, one trig function, arguments are all theta. Should allow me to solve this. Okay, now what? So when you look at this, it's still pretty confusing here. It doesn't look anything like that previous problem, which was a little clearer and straightforward. So how do we solve this? This is a quadratic trig equation. And what you should do is get everything on one side. Let's move everything over like you would for any quadratic equation. So I'm moving these 2 items to the left side. The reason I'm doing that is because that makes the quadratic sine squared positive. So on the left side is 0, just like you should for any quadratic equation. Let's start off with the highest power of sine, which is 2 sine squared. Let's talk about the sine itself, which is the linear term, and then 2 minus 1 is equal to 1. Now what? Well, I have a good method to solve this, and that would be, why don't you replace the trig function with a placeholder? Let's let something equal that, maybe u, or x, for that matter. But why don't we let u equal the trig function? It has to be the same trig function, which they are, has to be the same argument, which they are. And if you do that, look what we end up with. Now, I hope you're in very familiar territory now. This is a quadratic equation. And a quadratic equation wants to be solved, and one way to solve it is by factoring. There's only one good way to really make that 2u squared, and that's a 2u and a u. There's only 2 ways, really, to make the 1 here in a factorable sense, and that's 1 times 1, or how about minus 1 times minus 1? And you'll notice that the middle term worked. Negative 2u minus 1u is minus 3u. So we have factored this successfully. Continuing along those lines, we set each factor to 0, and look what we're going to get. Here, we get 2u equals positive 1, or u equals positive a half, and here we get u equals positive 1. So while we wish we were done, we're not. We have solved for u, actually. We've done a good job of that, but we need to finish this up. And to finish this up, we need to solve for theta. And the way to do that is to replace back in for our trig function. So let's replace back in for u. So let's see what u was. looking back, you can see that u was sine theta. So this is a good place to be, but we do need to finish this. Instead of u, we're going to put sine theta. Instead of u, we're going to put sine theta. Now, whenever sine or cosine is 1, -1 or 0, you don't have to do much trigonometry to figure that out. Simply graph a sine function here, and you'll discover, boy, there's only one place where sine is equal to +1, and that's right here. I wonder what that is in radians. Well, if a full circle is 2 pi, the middle is pi, that must be pi over 2. So we've got our first solution pretty much right away. And if you want to show all the solutions, don't forget the repetition. 2 pi n gives us that repetition and represents all of the coterminal angles. Now, it says sine is plus. So once again, just like the previous example, all students take calculus. Now, if it said sine is negative, wouldn't we go down here? But it says sine is positive, so we go here and here. The sine of the little reference angle is the number part 1/2 by memory. I know what that is. It's 30 degrees or pi over 6. Now, it's simply a matter of paste and measure into those two quadrants. Let's put pi over 6 here. So the first answer would be pi over 6 itself. Let's put pi over 6, remember, measure up against the x, not the y-axis. And then we measure to this angle here. But remember how I did that? I said, hey, what if you went too far? If you did, you would have gone a half a circle or pi radians. But that's too far, so back off by pi over 6. So that's 6 pi over 6 minus 1 pi over 6, or 5 pi over 6. So here are the three principal answers. Let's not forget to add the 2 pi n to get our repetition. So there you have some very concrete examples of how to solve trig equations. You do want all the trig functions to be the same. You do want the arguments to be the same. Use identities to help you with that. Once you do that, you can actually let u be equal to that trig function. And if it's a quadratic, solve the quadratic equation first, then put the trig function back, and then solve each trig function independently, trig equation independently. There normally are 2 answers per trig equation. So sometimes you can get 4 answers because you have, you're factored, so you got 2 different trig equations in that example. Okay, the last video for section C3 will be coming up next, and we're going to be discussing graphing trig functions. So stay tuned. We'll see you shortly.